Human language is highly compressed. We rely on shared assumptions, cultural context, and implied tone to communicate efficiently. That density makes human communication incredibly rich, but it also makes it inherently hostile to computation. Machines require discrete mathematics. To a human, this phrase is a fork in the road. We resolve the ambiguity by looking at the previous sentence, the speaker's history, or even a facial expression to distinguish a sincere compliment from a biting insult. The machine's initial view contains no intent, no sentiment, and no humor. It registers a meaningless string of ASCII characters. Before an algorithm can derive mathematical meaning or intent from that text, it must first force the unstructured data through a rigid pre-processing pipeline. Text pre-processing is the mechanical baseline. It normalizes chaotic inputs into uniform data structures, so modeling can actually begin. Tokenization slices the text string into individual computable units, severing punctuation from words. Next, lemmatization reduces tokens to base dictionary forms. Outdone becomes outdo, minimizing data sparsity. Finally, named entity recognition categorizes specific tokens as distinct entity types, like people or places. Early natural language models, utilizing Bag of Words or TF-IDF, stopped here. They treated these isolated tokens as raw frequency statistics, completely ignoring the sequence in which they appeared. Simply counting token frequency does not equate to understanding language. To move forward, computer science had to transition from tabulating word counts to analyzing syntactic structure. Deducing basic meaning requires extracting the structural relationships from the tokenized sentence. A constituency parse tree models syntax by grouping words into nested layers of noun and verb phrases. But dependency parsing instead identifies directed grammatical relationships, charting clear arcs directly between headwords and their dependents. These parse trees successfully reveal the grammatical skeleton of a sentence. However, they remain entirely blind to the actual semantic definitions of the words themselves. Explicit grammatical rules break down under the weight of human linguistic variation. Deep language processing requires mapping the continuous relationships of meanings, rather than just categorizing discrete grammar. While parse trees map how words relate structurally, they are deaf to what those words actually mean. To solve this semantic blindness, the field moved away from rigid rules and toward continuous vector spaces. Word embeddings like Word2Vec transform text tokens into multidimensional numerical vectors, plotting a word like brilliant as a specific mathematical data point. The core theorem is that spatial proximity equates to semantic similarity. Brilliant clusters tightly alongside genius, positioned far from stupid. The critical flaw in early embeddings is that they are static. The vector coordinates for brilliant remain mathematically identical, whether used as a sincere compliment or a sarcastic insult. Without the ability to dynamically alter a word's mathematical representation based on its surrounding context, static embeddings cannot capture human intent. The solution to the static embedding bottleneck arrived with the transformer architecture, notably models like BERT. Previous architectures, like RNNs, process text one word at a time, creating a computational bottleneck where early information frequently vanished before the end of a long conversation. Transformers eliminated this by processing entire sequences simultaneously. Because the model no longer waits for word 10 to finish word 1, it maintains parallelized context across thousands of tokens in a single pass. This self-attention heat map represents the core innovation of the transformer, mathematically weighting the relevance of every word against every other word in a sequence. Notice how the connection weight intensifies specifically at the intersection between brilliant and a prior negative phrase. By drawing these connections, the model calculates that the local positive sentiment of the current sentence is actively subverted by the history of the conversation. By mathematically modeling exactly how words attend to their neighbors, natural language processing successfully transitioned from analyzing isolated syntax to understanding global conversational context. Sarcasm detection in multi-turn conversations serves as the ultimate modern benchmark for testing a model's contextual awareness. Consider a baseline experiment, a logistic regression model attempting to detect sarcasm using only TF-IDF token frequencies. This confusion matrix plots the actual versus predicted results of the baseline model, producing dense clusters of false positives and false negatives. Translating this data into a precision recall curve shows the model hitting a hard performance ceiling with an AUC PR of 0.7. Sarcasm is a subversion of sentiment across turns. It is not a localized keyword. Shallow feature extraction completely collapses when linguistic intent contradicts the literal dictionary definitions of the words being used. Modern transformer models can solve the sarcasm problem using attention pooling across dialogue history, but proving that capability requires entirely new evaluation frameworks. These are the mathematical formulas for Blue and Rouge. While effective for measuring word-for-word translation accuracy, they fail to register sarcastic subversion because they cannot register intent, only the statistical overlap of characters. Both metrics strictly measure n-gram statistical overlap. This makes them blind to nuance, cultural bias, or multi-turn irony, where the exact words matter far less than the overarching tone. Proper evaluation of highly contextual deep learning tasks requires classification metrics like F1 scores, AUC-PR, and a rigorous accounting of dataset subjectivity. Modern NLP has mastered syntax and local semantics. The frontier is now capturing multimodal context, eliminating cultural bias, and building metrics that measure true human intent rather than mere statistical overlap.